Yes, I will try to summarize chapter 6, control charts for variables. For this part, x bar is the addition of the n items that are measured and divided by n. So let's try to summarize what we want to say with x bar. Let's say that we have a production line, and in this production line there are lots of products being produced, maybe from the machine. So we take random samples. We take random samples of n from here. So x bar 1, another random sample, x2 bar, another random sample, x3 bar, another random sample. So with the random samples we choose and take the average of how many samples we take. Each time we think that n samples are chosen. Later on we will see what happens to the control diagrams when the sample numbers change. So random sample is important. How to choose a random sample is important. Please note that human mind cannot choose randomly. We usually think about the system or a model to choose from a production. So we need to assign random numbers from the computer and then decide at what time will we go to the production line and choose the samples from. So, as we know from the central limit theorem, if we are choosing randomly n samples and if we're taking the averages of them, then the distribution of these averages are normal. So let's go to our summary of chapter 6. What does it say? X bar is normally distributed with mean mu and standard deviation sigma x bar is equal to sigma all over square root of n. So this is a really memorizable equation. Let x1 bar, x2 bar and xn bar be the average of each sample. Then the best estimator of mu and the process average is the grand average. What do we mean by grand average? As we said, we have the averages of every sample. We have one average here. We have two average, 3, 4. So when we take the average of all the averages, which is x bar bar, symbolized as x bar bar, equals x1 bar plus x2 bar plus going to xm bar all over m will give us the grand average. Thus, x bar bar would be used as the center line on the x bar chart. We will see how we calculate and use this. To construct the control limits, we need an estimate of the standard deviation sigma. Estimate of standard deviation sigma can be found by standard deviations of the samples or from the ranges of the m samples. So there are two ways. One is standard deviation of the samples and the other is range of the samples. What is range? Let's say we have taken 5 samples. From that samples, R is X maximum minus X minimum. So out of 5 numbers, we take the maximum number and subtract the minimum number from maximum number. That will give the range of that sample. Let R1, R2 and Rm be the ranges of the m samples. The average range is R bar, which is R1 plus R2 going to Rm all over m. Control limits for X bar chart. Upper control limit equals to X bar plus A2 R bar. Center line would be X bar bar, and lower control limit will be X bar minus A2 R bar. Now, what are these A2s? These are the calculated values, actually formed as a table. We know that the center line, from the center line we go 3 standard deviations up to reach the upper control limit and 3 standard deviations lower to reach the lower control limit. This is the short form of showing the numbers. Control limits for R chart are formalized as upper control limit equals D4 R bar, center line R bar, and lower control limit is D3 R bar. Where are these values? Where can we find them? We can find them from Appendix 6, page 702. So in Appendix 6, we see that on the very left column, we see that the sample numbers and these numbers A2, C4, D3, D4 are changing according to the sample numbers. So how many samples are we taking? Let's say that each time we're taking 5 samples. Then A2 would be 0.577, D3 would be 0, and D4 would be 2.140. So we will take the values from this table and put into the formula and find the values and then draw the control chart. Let's go to the example before going on to process capability. There was an example 6.1. So as we said before, we have taken 5 samples each time from the process. So we take the average of the 5 samples and take the range. How do we find range? We look at the maximum number here. It is 1.6914 and the minimum value is 1.3335. We subtract 132.35 from 169.14 and we find 0.3679. So for each row, we calculate the average and then we calculate the range and write for 25 times we have taken 5 samples, write each of them. So the grand total would be X bar 1, X bar 2, X bar 2 going on to X bar 25. We add all of them and then divide by 25 to find the grand average of X. And to find R bar, we add all the R's and then divide by 25 to find the R bar is equal to 0.3252. Sorry. So for lower control limit of R, we find R bar times D3. D3 is 0, so lower control limit for R is 0. Upper control limit for R is, we multiply D4 by R bar, which is 0.6874. Let's look at the diagram. So we find X bar here. It is found that X bar is 1.5056, same thing. So let's look at the graphs. We write the mean as the center line for X bar chart. This is X bar chart, and this is R chart. So as the center line, we write the mean, and upper control limit, lower control limit, we calculated from the equation X bar plus A2 is 0.577 times R bar, which is 0.3252. So when we multiply and then add, we find 1.69. 1.69 is the upper control limit for X bar chart, and 1.3179 is the lower control limit for the X bar chart. We first draw this line, then upper control limit line and lower control limit line, and then we point each X bar value onto the graph. So first one was, the mean is 1.506, and first X1 bar is 1.5119. So it's a little bit higher than the mean, so it's here. 1.4951 is lower than the central line, so it's lower the central line. So we will plot each 25 points on the graph. Since we are taking each sample in a time order, we put the points in a time order, and we see if there's a pattern or not, or if there are any points outside the upper control or lower control limits. So there are signs that we may expect the process to be out of control. We will try to look at these patterns. For example, going up and down, up and down, up and down would give a sign of a seasonal pattern. So we will look at these patterns in coming chapters. This was the example of 6.1, and I wanted assignments of 6.1 and 6.2. Now, process capability is very important to see whether our production is capable of producing qualified products. So process capability ratio we calculate with this equation: upper specification limit minus lower specification limit. Now we use upper control limit, lower control limit, and also we use upper specification limit and lower specification limit. Now what are these, and what is the difference between control limit and specification limit? The specification limit means what our customer wants from us as we are the producers. What are their limits? So at most they would like to have the production measurement, and at least they would like to buy, but lower than this, lower specification limit and upper than the specification limit, they wouldn't want to buy the product. So these are their limits. And Six Sigma, Sigma is our production. So upper control and lower control limits would be inside the 3 standard deviation of our production. I will show you the examples of process capability when we draw the line. For example, upper control limit is always what we target is the mu, and positive 3 sigma is upper control limit, negative 3 sigma is our lower control limit. So this is our production. This is so apart from upper specification limit and lower specification limit because these are the limits that our customer wants, but we may be producing a wonderful products so that we're mostly producing at the target and we're just going 3 sigma up and 3 sigma down. And their specification limits are so far away from the target that we sell all the products that we're producing. Let's look at how we calculate the CP, process capability. We subtract from upper specification limit. No, we subtract lower specification limit from upper specification limit. So this is the difference between them. And at the bottom we write 6 sigma there. So in our example CP is equal to 2. We go 3 standard deviation here and 3 standard deviation here, which will end up with 6 standard deviation. Again 3 standard deviation lower, 3 standard deviation lower. This places 6 standard deviation. So when we divide the upper specification limit difference to 6 sigma, it would be equal to 2. So this distance is 2 times more than this distance. So that's a really ideal and perfect production. For CP equals 1.5, it is not 2 times, but it is 1.5 times wider, these upper specification limits. So we are producing fine here also. For this production, the specification limits are so narrow or so close to the target, and we have a very bad actually production here because the standard deviations are so far away from the specification limit where our customer would like to buy the products between this space between upper specification and lower specification limits. So we are producing this much waste actually, which our customers wouldn't like to buy. So CP is equal to 1/2. So as we approach to 2, we get to ideal, perfect production. This is called 6 sigma. This is called 6 sigma, which is the ideal. companies try to reach this Six Sigma so that they would be selling all the products that they produce. So this is CP, and we will try to work on CP in chapter 8, maybe on Thursday. Since sigma is usually unknown, generally it is unknown because the process is changing, we must replace it with an estimate. So one of the estimate formula is range, average range all over D2. D2 is again a standard number for this equation. The quantity P is equal to 1 over Cp, Cp was the process capability, times 100%. Now, what is the solution? What is the result part of this equation? It is the percentage of the specification band that the process uses up. So, when we calculate, let's say, this, how much of this wideness do they use here? When we write 2, here, it would be 50%. So the limits here are so wide, specification limits, that our production only uses the 50% of all the wanted items. So we're producing at a 50% area. So let's summarize again what upper specification limit and lower specification limits are. They are the customer's criteria, and upper control and lower control limits are our production, plus or minus 3 sigma, 3 standard deviation. We went through this. So there is revision of control limits and center lines. The effective use of any control chart will require periodic revision. So we need to revise the control diagram periodically, and we need to revise the control limits and center lines. Regular periods may be weekly, monthly, or every 20, 50, or 100 samples. So company will decide the frequency of the periods. Interpretation of X bar and R chart. This is very important. Control chart can indicate an out of control condition even though no single point plots outside the control limits. So let's look at our example. We saw that there wasn't any point out limits. When you see this point, actually this is not out of the limits, but it's just under the upper control limit. But although there isn't a point outside of the limits, this kind of going up, down, up, down, up, down may show that the system, the process is out of control. Something is going wrong. I mean, giving a very low value and going up the center line. So these may be signs that show us that the process is out of control. This is saying that so plots outside the control, even though no single point plots outside the control limits, if the pattern of the plotted points, as I said, exhibits non-random or systematic behavior. So this may seem a systematic change in the production, which we wouldn't like to see, because we would like to see a random plot here, so randomly, without seeing any system. The goal of statistical process control is reducing variability. So let's look at this chart again. This is variability. So as much we lower the variability and push the values to the target, we have a better production.